model a tech-based gas dehydration process. In this video, we'll be able to model a tech-based gas dehydration plant and determine the water dew point of the product gas. You will also analyze hydrate formation conditions of various process streams around the dehydration process using the aspen hysys hydrate formation analysis. At the wellhead, reservoir fluids generally are saturated with water. The water in the gas can present some problems. Water can condense in the pipeline, leading to erosion. Water along with H2S and CO2 can cause gas corrosion and the formation of hydrates that can plug valves, fittings, and pipes. Generally, a dehydration unit is used in gas plant to meet a pipeline specification. While there are several different processes available for dehydration, triethylene glycol (TEG) is commonly used for natural gas dehydration where low dew point temperatures are required. This video includes the following tasks. Task 1. Define the feed streams. Task 2. Saturate the dry gas feed. Task 3. Add the TEG contactor. Task 4. Add TEG regenerator and makeup operation. Task 5. Perform water dew point calculation. Task 1. Define the feed streams. An important first step in this video is defining the components and thermodynamics model to be used in solving the process flow sheet. Aspen hysys provides a specialized glycol property package for use in modeling TEG dehydration processes. This property package is based on the TST-2-SEM-TASSON equation of a state model and contains the necessary pure components and binary interaction parameters for components commonly encountered in natural gas dehydration processes. The property package has been tuned to accurately represent the phase behavior of these components, and in particular, the TEG water binary system. Start a new case by clicking Create New Case. Click the Add button on the Component Lists folder to create a component list. Specify the following components to your component list. Select the Fluid Packages folder and create a fluid package. Choose Glycol package from the list of property packages. Click the Simulation Environment button to enter the simulation environment and begin building your free sheet. Add the material stream for the inlet gas. Change the name to inlet gas. Set temperature to 30 degrees centigrade and set pressure to 6,205. Set the molar flow to 498.1. Go to the composition page and enter the following composition. Add a second material stream. Change the name to TEG feed. Set the temperature to 50 degrees centigrade. Set the pressure to 6,205. Set the standard ideal liquid volume flow to 0.4543. On the composition page, change the composition basis to mass fraction. This concludes the first task. Task 2. Saturating the dry gas feed. Compositions of natural gas streams are often provided on a water-free basis. To ensure proper water saturation, the gas is mixed with some amount of water prior to entering the thick contactor absorption column. In order to do this, the saturated unit operation extension will be used to ensure the proper amount of water to saturate. From the model palette, choose Saturate with Water unit operation. Complete the Saturate with Water operation connections. Change the name to Feed Saturate. Set the feed stream to inlet gas. Name the product stream Gas to Contactor. Name the water stream Water to Saturate, noting that no parameters need to be specified for the water stream. Open the gas to contactor stream and go to the Attachments Analysis form. Click the Create button and select Hydrate Formation. Select the Performance tab to check the results. We can see that the hydrate formation temperature is about 18 degrees centigrade. This concludes the second task. Task 3. Adding the tech contactor. Add an absorber column from the model palette. Name the column Tech Contactor. Change the number of stages to 8. Set the top stage inlet to tech feed and the bottom stage inlet to gas to contactor. Name the overhead vapor outlet dry gas. Name the bottom's liquid outlet rich tech. Click Next. Set the top stage pressure to 6,191 kilopascal and set the bottom stage pressure to 6,205 kilopascal. Click Next, then click Done. Click Run. The column has converged. Add a valve. Set the inlet to rich tech. Name the outlet low pressure tech. Don't enter a pressure drop or outlet pressure, as these items will be back calculated from the next unit operation. Add a heat exchanger. Name the heat exchanger. Lean rich heat exchanger. Name the tube side outlet regenerator bottoms. And name the tube side outlet lean from lean rich. Set the shell side outlet to low pressure tech. And, and name the shell side outlet regenerator feed. On the parameters page, set the heat exchanger model to simple weighting. Set the shell side delta P to 69 kilopascal. And set the tube side delta P to 69 kilopascal as well. On the worksheet tab, set the region feed temperature to 105 degrees centigrade. And set the pressure to 110 kilopascal. The regenerator feed stream is now fully defined. This will enable you to build and solve the next unit operation, the TIG regenerator column. The tube side streams, regenerator bottoms, and lean from lean ridge will solve after the regenerator calculates. This concludes the third task. Task 4. TIG regeneration and makeup. The TIG regenerator is simulated as a distillation column. In practice, many glycol regenerator units are skid-mounted items and consist of some separation volume and the simple boiler unit for the introduction of some heat duty. In aspen hysys, this TIG regenerator unit will consist of a condenser, a boiler, and one theoretical stage. Add a distillation column from the model palette. Name the column TIG regenerator. Set the number of stages to 1. Set the outlet stream to regenerator feed. Keep the outlet stream stage to 1. Change the condenser type to full reflux. Name the overhead vapor outlet sour gas. Name the bottoms liquid outlet regenerator bottoms. Name the condenser energy stream. And name the boiler energy stream. Click Next. Keep the default boiler configuration. Then click Next. Set the condenser pressure to 96.5. and the condenser pressure drop to 7 kilopascal, and the reboiler pressure drop to 0, and the reboiler pressure to 103.5. Click Next. Leave the temperature estimates blank. Then click Next. Click Done. Select column temperature. Select condenser. Specify a value 102. Add another spec. Select column temperature. Set the stage to reboiler. Enter a value of 205. Back to the monitor page. Set the reflux ratio to 1. Keep only the condenser and the reboiler temperature at the active specification. Navigate to the parameters page, and on the solver form, change the damping of the solver to adaptive. Please note that using an adaptive damping factor will result in faster convergence for this column. This is generally true for most non-ideal component systems like glycol water and amine water mixtures. Go to the Performance tab to check the percentage mass recovery of tech in the regenerator button streams. You should note that the recovery of tech in the regenerator unit is not perfect. There is a small amount of loss in the sour gas outlet stream, as well as back at the tech contactor in the dry gas stream. As a result, a makeup stream is required to ensure that the material balance is maintained. You will inject some fresh glycol solution into the process using a mixer unit operation. Add a material stream. Change the name to Makeup Tech. Set the temperature to 15.56 degrees centigrade. On the composition, change the composition basis to mass fraction and set the mass fraction of tech to 0.99. Add a mixer. Add Makeup Tech. And lean from lean rich to the outlet streams and name the outlet stream Tech to Bump. Change the automatic pressure assignment to equalize all. On the Worksheet tab, set the standard ideal liquid volume flow Tech to Bump to 0.45 cubic meter per hour. A pump must be installed to raise the pressure of the tech before it re-enters the contactor. Add a pump. Set the inlet stream to take to pump and name the outlet stream pump out. Name the energy stream. On the worksheet tab, set the pressure of the pump out stream to 6,274 kilopascal. I have rearranged the flow sheet to make it easier to follow. Now a second heat exchanger is needed to cool the lean tank returning to the contactor to provide the cooling. You will use an existing process stream rather than some cold utility. The dry gas from the tech contactor will provide the cooling in this case. Add a heat exchanger. Set the tube side inlet to pump out and the tube side outlet to take to recycle. Set the shell side inlet to dry gas and the shell side outlet to sales gas. On the parameters page, set the heat exchanger model to simple weighted and set the shell side pressure drop to 34.5 kilopascal and the tube side delta P to 69 kilopascal. On the worksheet tab, set the take to recycle temperature to 50 degrees centigrade. The lean glycol inlet to the TIG contactor, which was originally estimated when the flow sheet was being built, will now be replaced with the newly calculated lean TIG. Using a recycle operation, you will close the TIG loop and the contactor and regenerator will recalculate until the recycle loop converges. Add a recycle operation from the model palette. Select TIG to recycle at the inlet stream and select TIG feed at the outlet stream. Switch to the parameters variable page. Enter a sensitivity of 1 for the flow and the enthalpy variable. And enter a sensitivity of 0.1 for composition. This concludes task number 4. Task 5. Water dew point calculation. One of the criteria used to determine the efficiency of a dehydration facility is the water dew point of the dry gas. This can easily be checked by finding the temperature at which water will just begin to condense. First, all traces of TIG must be removed from the stream being tested because TIG can affect the water dew point calculation. The most efficient means of removing the TIG is through the use of a component splitter unit operation. The resulting stream can then be analyzed in order to find the point of water formation. Please note that the component splitter doesn't use a rigorous phase equilibrium flash to separate components. The separation is specified by the user. Add a component splitter from the model palette. Name it remove tick. Set the LH stream to sales gas. Set the overhead outlet to tick only. And set the bottom's outlet to sales gas no tick. Name the energy stream. On the parameters page, set the temperature of tick only stream to 30 degrees centigrade. And the sales gas no tick temperature to 30 degrees centigrade as well. Set the pressure designation to equalize all stream pressures. On the splits page, set the tick glycol of the tick only stream to 1 and all other components to 0. Remember that water dew point is not a standard reported property correlation in hysys. If you wish to view the water dew point of a given material stream, you must add it to the stream via its properties form. Open the property view of the sales gas no tick stream. Select the properties form. From the property correlation controls, click the append new correlation. Expand the gas group and select water dew point. This concludes the last task in our video. Thank you for watching.